while I was checking homework, did everybody get one? Sometimes I skip people.
Yes.
Awesome. All right, so on the Friday before our little bitty break, we defined logarithms as log base b of a equals x if and only if b to the x equals a. And that makes sense. What we didn't deal with at all on Friday was anything that was in base e. Base e is the natural base. And so when we take the log of the natural base, we call it the natural log. And we talked about its importance and how it's used to model so many things, that log e, or log base e, is so special that it has its own notation. And it is ln. And the reason it's ln instead of nl, because you would think this is natural log. It's actually from the Latin, logarithmus naturali. You know, in almost every other language, they put the adjective after. And so in English, we like to mess everything up. And so it doesn't make sense to us, but it makes sense for when it was named.
ln stands for.
So ln is natural log. So instead of writing log base e, we never write log base e, we just write natural log. Okay. So let's try 1, 2, 3, and 4. You're just switching from exponential to logarithmic form of these equations. Give it a try.
Yeah, baby.
Let me know if you have questions.
Do you have to use the ln form when you're doing the?
When it's base e,
Yeah.
you must.
So like e is like e to the x equals a isn't a thing. You can't use that.
You exponential form, you can write it like
Oh, I
that.
meant sorry. Like, okay,
But if we're
yeah,
switching from exponential to logarithmic, we would have to use natural log.
how do you?
Oh.
Okay, so this one would become log base 2 of 8 equals 3. A logarithm always solves for the exponent. All right, so this is log base e of 4 equals x. But log base e is always written as natural log, ln. ln of 4 equals x. All right, this becomes log base 2 of 1/8 equals -3. This becomes log base 10. Do we need to write a 10 when it's base 10?
No.
No, because that's the common log. So log of 1,000 equals x. Now, on this one, this is nice because this solves for x. This is the exact solution right here for x. If I asked for the exact answer, you'd say x equals ln of 4. But did you guys notice there's a natural log button on your calculator right below the log button? We could come up with a decimal approximation for this also if we punched in ln of 4. And so this is approximately, this is not the exact answer, but if we were solving this, you could say it's approximately 1.386. All right, this one we could also use our calculator for because this is common log, but do we need a calculator for what power we raise 10 to get 1,000?
No.
No. We could simply solve this knowing that that is 3. Now these did not ask us to solve, I just added that at the end. So we were just to convert from exponential to logarithmic form. So this is truly the answer we were looking for here, and it's also the exact answer to that solution. This is the answer we were looking for here too. just where we switch forms. Okay, so this goes the other way. Start with logarithmic, give me exponential. So this would be 3 to the 4th equals 81. This would be, what's my base? X to the what power? Equals 216. And we know the answer to that is 6. All right, this would be 8 to the negative 3rd equals 1 over 112. And what is the base on number 8? E. So it would be e to the x equals 52. So the first 4 we're switching from exponential to logarithmic, and the second 4 we're switching from logarithmic to exponential form. Now, we know we can go back and forth, and when we think about the connection between exponentials and logarithmic functions, we know that logs undo or solve for our exponents. Therefore, when we think about them in terms of functions, how can we classify them?
They approach an asymptote.
They do. They reflect over an asymptote. Their graphs are symmetric over, and we'll talk about that in a second, but what kind of functions are they? Inverse. I heard it. They are inverses of one
Better
another.
than anything you had, dude.
Dude,
I'm just trying to learn.
I said real, bro.
Was that positive?
Yes, it was.
I'm learning. Love learning.
All right. So the images of their graphs, if they're inverses. All right, Sammy. If you try.
That was.
I
I
was
said.
just trying to.
I was motivating him.
If you
You
are
want-
trying to
Hey.
get him to lose his cool
Get the
and
camera.
be unpositive, which is negative, then everybody will get cookie cake but you.
Yes. And you make another one.
Oh.
All right. So the graphs of inverses are symmetric over what line, guys?
Y equals X.
Yes. Y equals X. Okay. So let's think about the inverse of these exponential. We know they're going to end up being what kind of functions? Logarithmic. So remember our steps for finding inverses. Step 1 is we switch the x and y, and step 2 is we solve for y. 2 steps. Okay, so step 1 is to switch the x and y, so we get x equals 2 to the y, and now we solve for y. Now we solve for an exponent. How do we solve for an exponent? We use a log. So it becomes log, what's your base? 2, what's your answer part? Equals the exponent. And I'm going to let you know it's an inverse by using the inverse notation there. So the inverse of y equals 2 to the x is log base 2 of x. All right, you try 2, 3, and 4.
Linux.
All right, take a look at 2, 3, and 4. How'd you do?
100%.
Awesome. Okay, so since logarithmic functions are inverses of exponential functions, we're going to go back and take a look at the exponentials, which we've been working on recently, and kind of relate that to the log before we just focus on logarithmic functions. So here it says identify 5. We're going to go with 3. 3 is good enough. Identify 3 points that would be contained on the graph of y equals 2 to the x. Well, when we graphed exponentials, we did 3 points. -1, 0, and 1. And we always tested those on the parent graph after it had been transformed. Well, this is just the parent graph. So 2 to the negative first is 1/2, 2 to the 0 is 1, and 2 to the first is 2. So if we go back and graph this exponential function, we're quite familiar with it. We know it has an asymptote, and the asymptote is the x-axis. It is the line y equals 0. So we know it rides along this line. Approaching this line as x approaches negative infinity. And it's an exponential increasing function. Now, since we've already been talking about these are inverses of one another, we know with inverses it switches the x and y's. So what do you think it's going to do with this little chart? It's going to flip-flop it, isn't it? The x's are now the y's, and the y's are now the x's. So we know that's what's going to happen. But let's think about if we didn't have this to start with. What could we do to determine this? Well, if we switch forms right here, we get 2 to the y equals x, don't we? So the easiest way to solve for x is to plug in values for y. So that's why we make our y -1, 0, and 1, because it's really easy to plug those in and get out our x's, because x is 2 to the y. So that's why we're going to use these values for our y's, and then when we plug them in, it gives us an easy x to follow. So we've got 1/2 -1, 1 0, and 2 1. So this one is going to have an asymptote also, but now my asymptote is the y-axis. Before it was the x-axis. So with exponential, we had a horizontal asymptote. With logarithmic, we have a vertical asymptote. All right, does it appear that is a reflection over the line y equals x?
Yes.
Pretty close. Mine's a little off, but yours probably looks a little better. That was not helpful. Okay, you try graphing y equals 3 to the x versus y equals log base 3 of x. Doesn't look much different, does it?
Just a little bit narrower.
Whoa. Oh, shouldn't have been curved like that. Okay, so with our exponential, we had a domain from negative infinity to positive infinity, but our range was 0 to infinity. So with the exponential, that's our domain, and this is our range.
Flip-flops.
It does. With the logarithmic, those are going to swap. And it makes sense that they do because they're inverse functions. So it is going to swap. So our domain is now from 0 to infinity. And our range is from negative infinity to positive infinity. Okay, let's take a look at this last one. This is how we're going to think about these because they're actually pretty easy to graph. What we're going to do is we're going to deal with any transformation first. And now, instead of shifting a horizontal asymptote with a logarithmic, we'll be shifting a vertical asymptote. So the shift left or right is going to move that vertical asymptote. On this problem, what's accomplished by that 1 in the equation? What does it do?
Moves it up
Right.
Moves it, shifts the asymptote right 1.
Yeah.
Okay, and I'm going to go ahead and do that. I'm going to draw this asymptote right 1 unit. There's my vertical asymptote. See, it was right there on that one. I didn't draw it in because I had the 2 graphs. But there's that vertical asymptote. Now let's talk about what that 3 does. What does that 3 do?
Your starting point shifts it up.
Shifts that starting point up 3 units. So we're going to shift that starting point up 1, 2, 3. So this is my new starting position. All my moves will come from this new position here. Okay, so now I dealt with that part and that part of the equation. So I'm really just looking at log base 2 of x, which if I equals y. So if I switch forms on this, this would be 2 to the y equals x. So when I'm thinking about my y moves, -1, 0, 1, 2 to the negative first is a half, 2 to the 0 is 1, 2 to the first is 2. You guys, you're welcome to do this part in your head. I'm just writing it out the first couple of times so we can truly see what's happening. And then after that, you can do these in your head. So from this starting position, I'll go over a half and down 1, over a half and down 1. Over 1 and up and down 0. Over 2 and up 1. And then here is my function. So it looks something like that. All right, tell me about the domain of this function. 1 to infinity is correct, non-inclusive. Range. Negative infinity to positive infinity. Now, the last thing it asks us for is the zeros. And like this one, you can see it. The 0 is +1. Up here, we have the same 0, +1. This one is not. This one's different. So sometimes we can't just look at our graph. Sometimes we have to solve to find our zeros. So if we have to solve, we go back to that original function and we want to know where it equals 0. So 0 equals log base 2 of x minus 1 plus 3. What we want to do is get this in logarithmic form. And to do that, we got to get rid of this extra. We got this plus 3 added to the end. What can we do with it? Subtract 3. Great idea. So now we have -3 equals log base 2 of x minus 1. It's in log form. There's nothing else we can do with log form. And here's my trick. Whenever I'm in one form and I've done everything I can do, I switch forms. So let's go from logarithmic to exponential and see if that helps us. So in exponential, what would it look like?
2 to the -3 equals x minus 1.
Oh, that did help. Because 2 to the -3 is just 1/8, right? Reciprocal, 2 to the 3rd, 8. And how do we solve for x? Add 1. So 1 1/8 is my 0, isn't it? This function has a value of 0 when x equals 1 1/8. Doesn't it look like it's really close to 1?
Yeah.
Yeah. So when it crosses perfectly, when you get a dot in the crosshairs, You don't need to solve for it algebraically. You can see it. But sometimes it doesn't cross perfectly. So we would solve for it. Okay, we're going to do these two together. And then the rest of the back is for your homework. So let's knock these two out and give you a little bit of time, hopefully. All right, what's the base here, guys? E. Okay, cool. Let's deal with that shifting first. That vertical asymptote shifts how?
Left 3.
Left
up
3,
2.
and then up 2 with our starting position. So our starting position is left 3 and up 2. And my base is E. So if E is my base, E to the negative 1 is 1 over E, which is about 1 over 2.7. E to the 0 is 1. E to the first is about 2.7. Because remember, when we ignore the transformation part and convert this part, this becomes E to the Y equals X. That's how I found all of these. And we know that E is approximately 2.71828. 2.7 is good enough. All right, so from my starting position, I go over about a third and down 1. About a third, down 1. Go over 1, go over 2.7-ish, and up 1. And there's your graph.
It's just, if it's a negative log, does it flip it over the?
We're getting there. There's two kinds of negatives. We're going to talk about this one and this one. We got two types of reflections. One's over the x and one's over the y. All right, this one, the domain is what? Negative 3 to infinity. The range? Negative to positive infinity. Okay, now did this cross perfect? No. So to find the zeros, we're going to have to solve them algebraically. So we're going to say 0 equals ln of x plus 3 plus 2. If it's a horizontal shift, it's going to be in parentheses with that x. Otherwise, like this one, is that negative 2 in parentheses? No, so it's a vertical. All right. So we're going to move that 2 over so we can get it in logarithmic form. And once we have it in logarithmic form, we can switch forms. What's my base? E. What's my exponent? Negative 2 equals, what's my answer? X plus 3. So we subtract 3 and we get that x equals e to the negative 2 minus 3. Or you could write that as 1 over e squared minus 3. Because e to the negative 2 is 1 over e squared.
Is that the 0?
That is the exact 0.
So you have to write it like that if you keep it in negative exponent.
Normally we would write it like this. I don't know that I'd count it wrong. All right, number 13. Is the asymptote shifted? Yes. Left 2. Is my starting position moved up or down any? Nope. So I'm starting right here. What's my base? 5. Negative 1, 0, 1. So this would be 1/5, 1, 5. Because my base is 5. Here's my exponents, right? 5 to the y equals x. Now, this one has a negative out in front. A negative in front of the function, of the entire function, negates the function, which is the y's. it causes a reflection over the x-axis. A negative in front of our x negates the x's, which causes a reflection over the y-axis. This changes all our y's to the opposite. This changes all of our x's to the opposite. So instead of going over a fifth and down 1, we go up 1. And instead of going over 5 and up 1, we go over 5 and down 1. So this logarithmic function now looks like that. Did it cross perfectly for my 0?
Yes.
Yes, it did. That was very nice. So my 0, I can truly see, is right here at -1. But if we solved algebraically, guess what we get? -1. What's the domain?
Negative 2
-2 to infinity? Range?
-infinity.
You got it. All right, guys, you've got the rest of class. So about 7 or 8 minutes to work on the rest of that back. Now, the calendar actually says there's also bookwork. I've decided to eliminate that part of the assignment for tonight, just the worksheet.